So let's go on. Our next talk is going to be given by Sharon Bottis on thermospheric gravity waves.
Hi, I'm going to be, well, first of all, before I even begin this talk, I want to thank Dave for inviting me. And also, I want to reiterate the fact that the work by Colin Hines was spectacular and has heavily influenced hundreds and hundreds of people around the globe to this day. And still, when I go to conferences all over the world, people come up to me and show me a wiggle in their data, and they say, "This looks like a gravity wave. Where is it from? What's its source? What am I looking for?" And so it's very exciting that I'm part of this workshop. And just know, Colin, that your work has influenced probably hundreds, maybe not even more than that, people worldwide trying to understand their data to this day. So this talk was originally, I was just going to show Mike Nichols' AGU talk, and so he was going to be first author, and I was just going to show it. But then I realized I couldn't really do that because his talks are very technical in terms of the observing side, and I wouldn't be able to tell you what the red and the green lines were. And our collaboration is theory and observations, and so I decided to reorient it and show my own talk. So, based on some of my stuff as well as mostly the new Irisuba Observatory data that he analyzed. So first of all, what has happened over the past 5 decades at Irisuba Observatory has been high-resolution single-beam measurements of gravity waves, which are just look straight up, single beam, and you can get vertical wavelengths from that. The observation has been made that gravity waves are always there, and you're looking at electron densities, and so these are the TIDs. And they're omnipresent, and they typically appear as wave packets. You see a few cycles, and then you see something else, it's a few cycles. And the other observation is that the vertical wavelength of the spectrum, if you add up all these gravity waves, they increase exponentially with altitude. So as you might well imagine, having only one beam gives you no horizontal information, so you can't actually get any source information directly from the observatory, from the instrument, but some speculations have been made. So given the wave packet nature of gravity waves in the thermosphere, and I want to emphasize that it's the thermosphere that seems to have very much wave packet looking nature. The mesosphere, often you'll see wave trains go for hours and hours, so those look more like steady state. But given the wave packet nature, another gravity wave dispersion relation, which includes viscosity, was derived and published in 2005, Bottis and Fritz paper, and that allowed for the ray tracing of gravity waves within a packet. So that's not a steady state approximation for that dispersion relation, and that's been used for convective plumes, etc. This lowest, I don't know how to use this. This lowest panel shows some figures from a 2007 paper. The dashed lines shows the Juth et al. Irisuba Observatory boxes of observations. The shaded boxes shows the theory using this dissipative dispersion relation, and the dashed dot line shows. The dashed dot line shows the Juth et al. Irisuba Observatory. The Oliver et al. Is the MU radar. And you can see that the shaded boxes, which is theory, fits pretty well. It's pretty well confined within the data. So the theory and data seems to agree pretty well here for a spectrum of gravity waves. And this is just ray tracing white noise gravity waves in a background atmosphere of 1,000 Kelvin, and launching them from the ground on the left and from 180 kilometers on the right. And I launched some from 180 kilometers because that is a source of secondary waves as well. That's an altitude where they can occur, either from momentum deposition or wave breaking or what have you. So one of the questions that I've been interested in over the past few years are the gravity waves in the thermosphere, do they just come and come and come and come? It's a steady state source of gravity waves in the thermosphere that are being observed, or are they coming in discrete wave packets? And a major difference between the theories is the wave packet theory. For an individual gravity wave, the vertical wavelength increases rapidly in altitude until the altitude where the momentum flux is maximum. And above that, the vertical wavelength could increase a little bit. That's the top in panel. You see that the vertical wavelength keeps increasing, but not exponentially, or it can decrease, or so it just depends on the background temperature as well as the wave that you're looking at. And whereas with the steady state theory, what steady state theory means is that you continuously pump the thermosphere with waves, the same horizontal wavelength, the same frequency, and you might pump it for hours and hours and hours, and then what happens is the solution to that situation is that the phase lines go pretty much vertical above the altitude where U prime W prime is maximum, and so that tells you that the vertical wavelength it increases exponentially. It becomes very large above Z-DUS. So these are new observations at Irisuba Observatory that Mike Nichols has analyzed and put together this campaign. It was 23 to 25 July 2009, and it's a 2-beam experiment. One beam was vertical, and one beam was off vertical, and the off vertical beam rotated 90 degrees every. We changed it, but typically every hour, hour and a half, 2 hours. And the bottom panel shows you the azimuth of that off vertical beam, so you could see that, when it rotated. And the rotation time at Irisuba was about 5 minutes, or 4. I think it was 4 minutes to rotate 90 degrees. So you might question some of the highest frequency, waves with periods of 5 minutes. Maybe we can't, get those very well, but anything over 10, 15 minutes, we feel that we could see those very well. So what you see in the data, that's the top two panels. The top panel is the vertical beam, and the second panel is the off vertical beam. And you see gravity waves, and you can see that you'll have a pulse of some gravity waves, and then it'll sort of change character as it seems like you have possibly a different packet coming along. And it's not a fixed plus minus, plus minus, plus minus feature that you often see, for instance, in Mike Taylor's mesopause pictures, where you have the same wave packet that appears to come forever and go for a really long time. So the thermosphere appears to be different, and anyway, that's been known for a while. But these very high resolution observations sort of show that as well. And some of the parameters of the waves that. So Mike analyzed that data and extracted waves, individual waves, and he found that the amplitudes of the waves of the TIDs is highest for waves that have periods 30 to 60 minutes, and there's an exponential increase for smaller periods. And then the top left panel, I don't know if you can read it, but the x-axis is lambda z, and the y-axis for all of the top panels is the altitude in kilometers, and it goes from 100 kilometers to 300 kilometers. So the bottom to the top is 100 to 300. So the observations span that range, and the black bar shows the mean, and the red dots show all of the waves, the observations that he extracted the parameters for. And what you can see for the vertical wavelength is that the vertical wavelength increases rapidly, exponentially, in the lower part of the atmosphere, the lower part of the thermosphere, excuse me, up until about 200 kilometers, and then it's only increases slowly above that altitude. And the second panel shows lambda H, and you can see that the waves in the lower part of the thermosphere have wavelengths of 50 to 100 kilometers, and then as you go up, the wavelength is more 100 kilometers to 1,000 kilometers. And so the periods also increase from 10 minutes up until 60 minutes as you go up in altitude. And the bottom panels show ray tracing theory using the Bottis and Fritz dissipative dispersion relation for wave packets. And you can see the general trend is captured in these simulations. So the red dots on the bottom are for ray tracing through zero wind, and the black dots on the bottom are for ray tracing through a wind which rotates 360 degrees in the mesosphere and has an amplitude of 100 meters per second. As I'll show you a few slides later, we found that the E-region winds are truly as large as Miguel Larson has been telling us for a long time. We're finding winds of 100, 200 meters per second in the E-region, neutral winds. So anyway, so we ray traced gravity waves through an entire, white noise gravity waves through an entire cycle of wind, so 360 degree rotation. And also that propagates the waves to much higher altitude. You end up weeding out the slower waves as well. So anyway, so the theory captures a lot of what the observations, a lot of the observations show. And this plot is maybe perhaps something that's very dear to my heart, which is Mike was able to extract the propagation direction of these waves because he's got this beam that rotates, and of course, if you have any technical questions about exactly how he did this, you should ask him. But if you have your beam pointing north and then you rotate it to east, and then you can get the propagation direction. But what he found, so the little triangles show the direction the wave is going. And so what you see is that the first day, July 23rd, most of the waves are going south and southeastward. Some of them are going northeastward. And there's pretty much nothing that day going, there's nothing going west at all. And there's a little bit going slightly eastward. And then on July 24th, the picture is quite different. It's more of an isotropic distribution, except you still do not have any westward waves, but you have a lot more waves going north, northwest, northeast, southwest, south, and southeast. And on July 25th, it's again a different situation. Looks a little more like July 23rd, but still different. You have a lot of waves going directly southeast. And then you also have a fair bit of waves also going northeast, north, and east. And so I just a reminder of where Arecibo is. Waves that would be going southward would be coming from Florida, the southern part of the United States, Alabama, that region in there. And waves that would be going eastward would be coming from the region of the whole peninsula, Mexico, Guatemala, that whole region, and then waves that would be going northward would be coming from the northern part of South America, and the islands in there. So this is work in progress to reverse ray trace these waves in order to try to identify their sources. We do this in collaboration with a meteorologist who identifies the convective plume sources for me. And then that's work in progress. So I can't actually say at this point where these waves are from, but they look like they're from deep convective sources. This is in the middle of July. This is when convection is very active, and these are daytime measurements. All right, so what about individual waves? Just to pop back, you can follow the phase lines up in altitude like we did previously, and as Frank Juth did as well in a 2010 paper. And you can convert the electron density perturbations to ion velocity using a very simple electron equation. And what we find is that so the markers, the color, there's overlapping colors, but if you try to follow a single color up, the left panel shows lambda z, and the next panel over shows the ion velocity, which is similar to a concatenation of the horizontal and vertical velocity of the gravity wave. It's the velocity that the gravity wave makes along the direction of the magnetic field line. And Mike has done this for individual waves. And so the left panel again is lambda z, and then the next panel is V ion. So if you look at a color, for example, dark blue. Dave, how do I use this?
There should be a triangular shape button.
Okay. So for example, let's look at this blue one here. Here's V ion, and you can see that V ion peaks at about 225 kilometers. So this is about the altitude. Somewhere in here is about the altitude where the momentum flux is maximum. And if you look over here at lambda z, you see that lambda z also peaks. It increases exponentially because this is a log scale here. Increases exponentially, but above the altitude where the gravity wave is maximum, the amplitude is. Lambda z doesn't really do much above that altitude. It's pretty much constant, and it certainly doesn't shoot off to very large values. You can look at other colors as well. These the size of the marker represents the TID amplitude, the electron density perturbation. So there's other examples as well. You could just see the general trend that this is true, and these are for different days, July 23rd, and then this is July 24th. So here's another easy one to see. This is the blue line, and it peaks at about 200 kilometers, and lambda z peaks there as well. So this fits better with the wave packet description, which shouldn't be very much of a surprise given the data that you saw 3 or 4 slides ago, which also showed wave packets. All right, and the last thing, this is not exactly a gravity wave thing, but it influences gravity wave ray tracing significantly, substantially. So I thought I would show it here. And this is that Mike was able to extract the E-region neutral winds from the Irisuba data, the beams. And so he was able to get the zonal and meridional components. And the right-hand panel shows the wind direction as a function of azimuth, and at different altitudes, 105, 110, 115, and 120, and for different days, depending on the color. And what you see is that the winds generally rotate clockwise in time, and if you can't read this scale, this is 200 meters per second. So this is the wind magnitude over on this column, and so the winds have magnitudes of somewhere between 50 to 200 meters per second over Irisuba in the E region, and they're massive. And of course, this is, I shouldn't say of course, but this is not something that the global models can capture. And but it's very important for filtering out waves from the lower atmosphere. You wipe out a lot of waves when you have winds this big. So again, future work is being done to understand the consequences of such large winds on waves from convective plumes that we're going to forward model in the future. So that's it. Thank you very much.
Questions for Sharon? John?
Hi, Sharon. Thank you for a very nice talk that I was able to follow. I was wondering about the identification of ocean waves as being the source function for the gravity wave he reported on in his observation of waves in the lower E region. It seems to me that perhaps with those waves going down to the southeast, that the origin might well be in the ocean, in the Caribbean, to the north of the island. Would you comment, please?
So are you going back, you're referring to the Juice et al. 2010 paper. I just want to make a quick comment, which is that the direction of propagation on that night was determined one data point. It was just a single wave, and it was seen in the, I think it was seen in the 6300 line. So it wasn't actually an Irisuba observation. So, you know, and also it could have, you know, could conceivably have been a Perkins instability wave. So I'm just going to say it and leave it. In terms of these waves here, ocean source is always a possibility. And when I do the reverse ray tracing, I'm going to be looking at all possibilities. Certainly, we know that tsunamis create gravity waves, so there's no reason that it couldn't be a source. So all possibilities are there, but certainly it looks like a lot of the waves are likely convective, but doesn't mean that all of them are, and we'll see.
That's a nice talk. I just have a question. I was wondering, so that say you, from the observations, based on the 3 days, what is the typical gravity wave amplitude when it reaches to like altitude 200 kilometers?
Yeah, tens of meters per second in terms of horizontal vertical velocities, typically 20 meters per second, 40 meters per second. If you want to know delta n, or are you looking for the electron density scaled amplitude? That's like a few percent. It's a few percent, 5%, 10%.
Yeah, because if you do a ray tracing and saying that those those waves were actually caused by the convective deep plume. So based on the because the wave amplitude is going to nearly increase exponentially, so the amplitude might be very large at 200 kilometer altitude, right?
Well, so when you talk about the convective plume, the big waves, the largest amplitude waves that are excited by a convective plume are gobbled up in the stratosphere. They have very large amplitudes. They're very small scale. They have horizontal wavelengths of 5-10 kilometers. They don't even get to the thermosphere. The waves that get to the thermosphere from a convective plume have humongous scales, and their amplitudes at the surface of the Earth are unbelievably tiny. You would never see them in any satellite. So the only way that we know that those waves are there is because their amplitudes grow exponentially. They're the only ones that get to the thermosphere because they don't break anywhere else because their amplitudes are unbelievably small. And then you can trace them back and you can infer that they were there, and you also know from models that they were there, and you match the two. And that's how we've realized that, yes, in fact, these big waves are excited.
Sharon, the waves you see at like 130 kilometers or so, what velocity, horizontal velocities do they have?
How do I go back? Like, I wasn't able to get it to go back. Oh, maybe you click on this thing right here. Keep going. One more. Wait, one more. One more. right there. Let's see. So 130 kilometers. The phase speeds. Is that what you're asking? The phase speeds, Jim? Yeah. The phase speeds are about 170 meters per second.
All right. So they're 170 meters a second. So they're going to be able to get through these
Yes.
large winds.
Yes.
But how come in the mesopause region, in our imagers, we rarely see stuff over 100 meters per second? So that's the thing that puzzles me. We rarely see these fast waves, but when you look in the thermosphere in the daytime over Arecibo, you see these fast waves, which they have to be fast to get through those large winds.
Yeah. I think that's partly, I don't know if that's something to do with the way that the data is analyzed or the fact that their amplitudes are so small you can't see them. There can be a lot of reasons that you don't
Well, that's why I asked
see them.
about 130 kilometers, because that's fairly close to the mesosphere.
Well,
And so
we could
I
maybe.
think it's a puzzle.
Yeah.
There are many scale heights between.
Yeah, there are.
30 kilometers.
Yeah, there are. So there, and as Dave pointed out, there's 40 kilometers between the OH altitude and 130 kilometers, and 40 divided by 8 is 5 scale heights, and e to the 5/2 is still a factor of, I don't know, 10, 15 or something like that. So it still has another 10, 15 that it can, it's multiplied by 10 or 15 times.
I was just
Just
going
looking at
to
this.
add that I don't know if we have any LiDAR people here from Irisuba, but of course, at least in the evening up to the sunrise, they're making wind measurements at sodium altitudes and so on, and able to pick out the spirals and so on for the propagating waves at whatever amplitude they would be from coming from below. So it'd be an interesting thing to look for as to if they are coming through that. That's a real puzzle.
Yeah.
I guess the other question I have was,
But
I mean-
just real quick, I just want to point out that the horizontal wavelengths of those waves from the same slide is something like 140 kilometers, and your field of view is 450. So you'd be looking for a plus and a minus covering your entire field of view, and you may or may not be comfortable with doing that, or that may or may not be easy to do as well.
we do pull those waves out of the imagers by other sampling methods.
Yeah.
But what I was going to say, I mean, it's a larger question here. I mean, we have well-known MSTIDs propagating throughout this, the thermosphere, often propagating ever-present, okay? So half the waves you were showing in the meridional context were or at least coming out of the northeast, which have that ever-present situation.
Going
So do you
towards
discriminate?
going towards the northeast. Yeah.
You had some going that way, and then you had some coming from the northeast.
Yeah.
From the
I guess that's
northwest,
true.
northeast.
Yeah. Yeah.
So, I mean, the suggestion is all of the TIDs that are being measured fall into this gravity wave signature, and do they have phase propagation with altitude that are consistent with the velocity? That's how you got the vertical, the
Yeah.
intrinsic phase speed.
Yeah, so all of them, we talked about this, and he only looked at those with the phase lines that descend in time. There are some quirky places where the phase lines look like they might go up in time. I'm interested in those regions because that may be downward propagating secondary waves, but it doesn't happen all that often, and we are not pursuing that in this paper. The ones that he did analyze are downward propagating phase lines, so upward going gravity waves.
I hate to curtail discussion, but I think we're in danger of losing people to lunch if we don't try to get our last couple of talks in. So I'd like to introduce, thank you, first of all, very much, Sharon, for a nice talk.